So yesterday we had defined the residence time distribution. We had defined the internal and external or the exit RTDs. And towards that, of course, we defined age or residence time and real time or T and an entry time T naught. So those are the basic independent variables. And then around those, we can think about distribution or probability density functions. And towards finding those functions, we had discussed an experiment where we would pulse a bit of salt into a reactor and then just watch the concentration at the exit point. And we found that the exit RTD could be estimated just by dividing the whole curve by the integral under that whole curve. So this gave us a really nice, practical, easy way to estimate an exit age distribution. And this development did not rely on any assumption. So we had not specified the nature of mixing. We hadn't specified whether it was CSTR or plug or anything like that. So we used no assumptions in developing this relationship, which means that it's nice and general. It means we can always do this. So no matter what reactor we have, no matter how complicated the reactor is, by the end of the day, we can always do this. We can always just stick a little pulse of tracer into our stream, and we can measure what's happening at the exit point. So we can just pulse in some tracer there, and we can observe a concentration trace there. And then we can perform this operation. And so there's no restriction. It doesn't matter what type of mixing we have here. It can be as complicated as we like. We can always do this procedure. And so we can always obtain an E of theta. So that's half the story. Then we started looking at the relationship between E and I. So we don't have any easy way to peer into this reactor. We want to treat it as if it's a black box and it's impossible to get data from. So in that approach, we have no easy way of measuring inside of that reactor. And so we developed an expression that related E and I. So because we know we can always get E, we can then stick E into the relationship and get I. And we did derive this relationship, but I think I was thinking about a slightly different approach to showing how to get this. So let's do this one again. I felt a bit like we waved our hands a bit too much around this one. So let's just do this one again. So say the flow rate is Q. And we, of course, we are interested in, we would like to estimate the fraction in age range. And this will be theta to theta plus delta theta. We would like to estimate the fraction in that specific age range. Then we can think about this range itself and recognize that it takes delta theta time units for this fluid to enter the reactor. So let's think about that in terms of perhaps some real numbers. So let's say, so we are saying we want to know in a specific age range, and let's call that 1 hour and 1 hour and 20 minutes. So we want to know what's the fraction that has spent this amount of time in the reactor. So in the reactor, different fluid elements spend different periods of time, and we want to know what fraction spends between 1 hour and 1 hour 20 minutes. So if we think about where that could have come from, right? So we are saying in the reactor, those fluid elements exist, but we can think back in time, when would those have entered? So if we want to know currently in the reactor, how much fluid has spent between 1 hour and 1 hour and 20 minutes, then we can say, well, if I look back in time, so if my current time is here, if this is my current time, if I were to subtract backwards to 1 hour, so T minus 1 hour, then that would be when the fluid elements started entering that reactor. And then if and then it ended when they were 1 hour and 20 minutes. So that's the other edge of it there. So in other words, we are thinking about the cohort of fluid elements and when they entered the reactor. So fluid that spent 1 hour in the reactor must have entered 1 hour earlier. So they entered here, and then, well, this one spent 1 hour and 20 minutes. So that entered even earlier. So that entered here. So minus 1 hour and 20 minutes is somewhere there. So that's the group of fluid elements. That's the time range for the elements of interest. And if you think about that, it took 20 minutes for that group to enter, right? We can think of all the fluid elements in the reactor in this time range. We can think of that as a group of fluid elements. There's a certain group of fluid elements in the reactor in this age range. And that group entered over a 20-minute period, just by virtue of the fact that that's the width of that range. So it took 20 minutes for that group to enter. And so the amount, the volume, if you like, of these elements must then be Q delta theta, right? It took delta theta time units for that group to enter, and the flow rate was Q. So that's the volume of these fluid elements. And you can say, yes, that's when, so if these elements are that old, that's when they entered. But these are not the only fluid elements that entered from that group. So 1 hour and 20 minutes ago, a certain group entered. But as time went on, some of that group was exiting from that reactor. In other words, not all of the fluid elements that entered back then are still in the reactor. Some did exit between then and now. So the amount that exited, between then and now, then being when they entered, the amount that exited between then and now, we can estimate, since we have an RTD, we have an exit RTD. So we can say E of theta, if we integrate that in theta, that's going to give us the fraction that appeared at the exit. And we want to know this over the specific range. So we want to know it between theta, let me just do it like this. So that's what we want to know, between theta and theta plus delta theta. So that is the fraction that, well, it's actually not just between then and there, it's the fraction of the entire fraction that exited is from 0. So when those fluid elements first entered, right, 1 hour and 20 minutes ago, when they first entered, they kept leaving the reactor. They kept exiting in this exit stream. And right now there are still some left over in the reactor. And that's what we are trying to figure out, how much is left over. But we have to acknowledge from the moment they entered, there could have been some that exited. And so from age 0, they were exiting the reactor and they were exiting all the way up to age theta. So that, if you like, is the fraction that exited over that time period. So between when they entered and now, when they are age theta, that's the fraction that exited. Remember, E of theta is defined such that E of theta delta theta is the fraction that exited between theta and theta plus delta theta. So now we are asking, what's the total amount that exited up to age theta? So we go from 0 to theta. So that's a fraction. whereas we want to work in volumes. So the total volume that ever entered was Q delta theta. So if I just multiply these two together, then that will tell me the volume that exited between then and now. And I must say, this is in a way the hardest step of this balance. Is this clear? Any questions or comments on this one? Okay, so just let me know if you want to look at that again, but I'll continue here so long. So, so the amount that's left over is, and it's going to be the amount that entered in the first place minus the amount that exited. Right, so that's what exited. But this is also equal to, right? So the amount that's left over is what's in the reactor. And we have defined the fraction that's in the reactor in a particular age range. So I of theta, oops, that's a capital beta. Let's keep doing this. Theta. Yeah. The I of theta delta theta, that is the fraction that's in the reactor in that age range. And so the total volume that's in that age range is equal to that. Right, so that's simply what's left over in the reactor from that cohort of elements that entered. So we can say, therefore, this equals this minus this. And in this, we can see the delta theta. We've got a delta theta everywhere. So let's cancel the delta thetas. Well, let's leave this one first and then, yeah. So delta theta, and we can cancel the delta thetas. So that's one thing we can do. And then you can see a common Q in here as well. So my equation is a bit messed up. 1 second. So that's what we have. And then we can group out this Q as well. So we can say here 1 minus this thing. Right. And then we recognize V over Q as a tau. So this is the same as I tau equals that, or we can rewrite it as I of theta equals 1 over tau times that 1 over tau. Right, so that's the I of theta we are looking for. Okay, any questions or comments on this part? Right, in a way, this this balance is somewhat too easy. It's there are very few steps, but there's one step where you have to scratch your head a little bit. Once you understand this part and a little bit this part, then the rest is pretty automatic. Okay, so that's the relationship that we have. And that's kind of the very mathematical way of looking at it. So now let's relax a bit and let's think if we could just guess what the RTDs look like for our different reactor types. So let's just so let's say this. Is this the 7th? Am I in the right folder? Right. So while I'm fiddling about here, think about how would this look for the CSTR, right, or the PFR, or the batch reactor? What's the RTD look like for those cases? Anyone like to try and guess what the RTD is going to look like for the CSTR? So I'll just draw some axes along. Right, so the CSTR, and I know some of you have done the prac, so you know what it looks like or have some ideas about what this should be. So here's the CSTR. Here is our set of streams. Okay, so anyone like to just mention what kind of shape you would expect to see here? And if you're feeling a bit hesitant about guessing there, what you could always do is imagine doing the tracer study. Remember that when we derived for E of theta, we said, oh, it's so easy. You just need to do C over the integral of C, right? Remember, we have this really nice, easy way of getting E of theta. Excuse me. So if we have this available, we could think about just do as a thought experiment. What if we spiked a bit of tracer in? So we put in some tracer, and then can we guess how that tracer is going to exit here? So in other words, what would the salt concentration change with time look like? Right? Anyone like to guess there? Okay, so let's say we've spiked ourselves with a bit of salt. And so let's think about initially. Well, initially, the concentration of tracer or the salt will be fairly high because it mixes instantaneously, right? That's the feature of CSTR. The moment we put something in, it mixes instantaneously everywhere. So immediately we start to see salt appearing at the exit. So we will immediately start to see some of that tracer at the exit point, right? But of course, we also have not fed any more tracer in, right? After we put tracer into this reactor, we don't put any more in thereafter. So now we are sitting here at this time, right? So at some time after the tracer has been introduced, then there's no new tracer in this reactor, no new salt there. So we are starting only to lose salt from this reactor. We've charged some salt in, that salt instantaneously mixed everywhere, but then we didn't feed any more salt into that reactor. That means when we are looking around this time point, this instant in time, only water is entering, no more salt is entering. So that water is going to dilute the salt in that reactor. And so our concentration is going to start dropping here. And it's a kind of serial dilution effect. As time goes on, more fresh water arrives, which has no salt. And so whatever salt is left over here is just going to get more and more dilute. And of course, there is still salt here. So salt will still be making it at the exit. So salt concentration is just going to drop slowly. And it's going to drop at an ever decreasing rate because the less salt you have, the less probability that salt molecules will make it to the exit point, right? So salt is being held up in the reactor and it is being drained out, but very slowly. So we expect some kind of exponential die-off in this reactor. So our E of theta curve, we expect an exponential die-off over here, and then we are dividing by the area underneath that. So the fact that it's an exponential die-off doesn't matter. The point is it is a decreasing, so it's a convergent die-off, and so the area under here is just some constant number by the end of the day. So this curve is going to be proportional to an exponential decay. So we expect from E of theta to have something like this. It's going to be an exponential decay. And so that's what we get for the CSTR. Okay, now what about the interior of the reactor, right? So this is what we are seeing at the exit. What is the age distribution inside of the reactor? How similar are these curves going to be? How dissimilar? Right, any takers on that?
Yeah, I think
yep.
the curve will look like an exponential curve.
So did you say you also expect an exponential curve there?
Yes, but a growth kind.
But on the growth side, so you are expecting it to go up like this. Is that what you're saying there?
Yes.
Okay, and then can you take us through your logic? Why would you expect it to do that?
I think it's because of the sudden introduction of the salt, maybe to cause some spike in concentration.
So it's I would agree with you as far as it's there's an exponential behavior I'm expecting. And yes, it's true that there is going to be an exponential, that the salt is going to appear immediately. But you see, the salt appears even more immediately than this. You see, this takes some period of time, whereas what we say with perfect mixing is it's absolutely instantaneous. It's not even exponential. It's even faster than exponential. It's instantaneous. So the moment the salt hits here, it's instantly up at these high concentrations. So I would say we actually start out here. You start from a high salt concentration, right? And remember what I is the age distribution inside of the reactor. It's saying how many fluid elements, how much salt do we have inside the reactor? And so in the case of the CSTR, remember, it's perfect mixing, which means the exit point as well. That means we have the same thing, the same concentrations inside of the reactor as at the exit point, right? So we will actually then get the exact same curve for the internal RTD. So you're right in the sense it's an exponential curve, but it's sloping the other way, because the part that you are talking about where the salt concentration goes up quickly, it's absolutely instantaneous. It immediately shoots up to that mixed concentration. But the amount that stays in the reactor is totally dependent on its exit flow from there. So we do keep losing salt, we keep losing fluid elements. So another way to think of this is if we look at the age distribution of the planet, right? So our age distribution. So people are born here and they're dying as well. And so as time goes on, the various factors that kill people off, those are always operating. So let's say you had an equal chance of dying at any age. So as you spend more time in the space, you are exposed to those same factors. Let's do it as I. So you entered the world. There's your entire, so there's the population of people that entered the world. And then these people were exposed to various factors that killed them off. So let's say at any instant in time, there was a certain probability of killing off someone from the population. And let's say it's a small number, let's say 10 to the minus 10 or something like that. Then after some time goes, a certain fraction of the population will get killed off, and there'll be a certain number left over. And then the same factors that apply, the same factors that were killing people off, that was still in operation. So after some further time passes, from this leftover population, more people die off. And then the same thing keeps applying. So we just keep killing people off. So in the case of our reactor, killing someone off is the same as them leaving the reactor. So remember, the counting age depends on the space. And so if you leave the space, we regard that as a death from the space. I'm not just saying that to be funny, right? In the field of population dynamics, they actually have birth and death terms. So yeah, you can talk about the death of a member from the population, which is simply an exit from this reactor in this case. So that is what happens here in our CSTR. Okay, so it dies off like that. Now, that's what we expect, okay? And we'll prove, we'll actually do a little mass balance and see if we can prove that this is what happens. Now, let's go further. Let's think about the PFR. If we have a PFR, I guess let's do this as a new one. So if we have a PFR, first off, what is the age distribution exiting this PFR? And we have to recognize it's a very different situation now. So we are going to pulse a bit of tracer in here. And we are going to measure a concentration of salt here. So how is the salt concentration going to appear? What kind of shape do we expect to see on this plot? Any takers there? Where's our friend from earlier? What do you think? What kind of shape might we get here? I think someone else unmuted there. Please go ahead.
Is it the decay kind of shape?
So let's think about the decay shape. Well, if you think about these plugs, there's no actual decay, right? In this case, we have quite a different situation, right? In the case of the CSTR, we had a decay because number one, the salt all entered at one instant, and that's the same situation here. All the salt will enter. But here, the salt was held up and it left bit by bit by bit by bit. And so it decayed its way slowly out, right? It died a slow death over here. Now we have a very different situation. Now, all the salt enters and it's entering in one plug, okay? So it all enters in one plug. Then sometime later, that plug has chugged its way down here and there's nothing like that anymore near the entrance. And so in the case of the plug, it's flowing as a plug. The same plug of salt is chugging its way down. It's just going straight down, and then it's all going to exit in one shot at the exit here. So that's the feature of plug flow. It's all going to stick together as one thing and all exit as one thing. So we expect in the case of the plug flow reactor that it's going to look like this. So no exponential decay, but just one discontinuous shot of it. So let's draw that again. So there's our E. And we said everything is going to stay together. Now, we can see in the plug flow case, it's not the case that everything is going to immediately be accessible at the exit, right? In the CSTR, fine, everything mixes so fast that it immediately appears at the exit as well. So you straight away start seeing salt. But in the case of the plug flow reactor, right, there isn't instantaneous mixing. In the case of plug flow, the plug is going to, as we said, chug along, and it's going to take a certain amount of time to reach the exit here. So it's going to mooch, and then appear here. So it's all going to exit, but it's going to exit at some specific instant in time. So we expect to see some kind of spike like this. And then we have here, we have 0, we have nothing appearing at any other time. Okay, so that's the kind of curve that we have here. Right, so that's what we expect in the case of the plug. We'll see nothing, and then at some point, everything will exit. So we'll see everything like this, and then we'll see nothing again. Okay, so that's what we expect at the exit there. So now how about for the internal one? What do we expect to see for I of theta? Any takers there? Right, so our friend from before, any thoughts on how I of theta will look this time? Well, if we go by what we saw for the CSTR, we got the same thing, right? We got E and I being the same. So we start to wonder, are they all the same? Is E equal to I somehow? And if we think about it, that's not really possible, because in the case of E, we are only ever seeing something out here when we cross this critical time, whatever that is, right? This critical time here, whatever this is. So if we look at this, it's not the case that there's nothing in the reactor before that critical time, right? Before that critical time, that plug was still in the reactor. So that plug was slowly chugging its way along, and fine, it was all concentrated in one plug. But if we just count up all the salt overall in this reactor, we would say, yes, there's a certain non-zero concentration of salt in that reactor. So this salt stays in the reactor all the way until this exit time. So that, and it's the same concentration. So it's the same plug. So it's the same amount of salt that's staying in the reactor until everything exits. So in this case, we can say that the salt curve looks like this. And yeah, actually, let's not make it confusing with the box. It's actually like this, right? So the salt, so the internal one for the PFR is going to be a fixed number, and then it reaches this critical time, and then then there's nothing anymore. In other words, once we've reached the exit, then we have no more salt in the reactor. We don't have any salt of a greater age than this critical age. After the critical age, everything has exited, so the internal amount is 0. Right, so in the case of the PFR, it's very different. We've got a spike here, and then we've got constant, and then a 0. So that's what we expect to get in the case of the PFR. So very different, right? The CSTR, we had 2 exponential decays. In the case of the PFR, we have 1 spike and 1 what's called a Heaviside function. So if you recall, I don't know if you've seen Heaviside functions, maybe in physics. So, and I'm just trying to draw these the same. Yeah. So that's CSTR and that's PFR, very different age distributions, okay? So this was all us just kind of guessing our way through it. Let's see if we can derive this. And in fact, right, you could say, well, isn't this all very practical and you need to take tracer? How are you possibly going to derive this? Well, I'm not going to, I don't have a reactor in my lounge, right? Contrary to what people think, I don't have a reactor in my lounge, so I need to do this mathematically, right? And for a CSTR, I mean, I am at liberty to develop a mass balance for the CSTR. So I can simulate the case of a tracer passing through a CSTR. So let's derive it for a CSTR by simulation. So the CSTR pulse tracer in, and let's call that component A. So our salt is component A. So we can happily write a balance on a CSTR. We can say dCA dt equals, and the balance of the CSTR, we know we can say C A in minus C A divided by tau, right? So all this is just the balance that you are familiar with from before. We would normally write here also minus RA, right? The reaction rate, but there's no reaction here, right? We are doing all this without a reaction because at the moment we are just trying to understand how long things spend in the reactor. So, and especially our salt, we are not bothered about our salt reacting. Our salt is not reacting in this reactor. So there's no reaction term to worry about. Also, the CA in is in a way a little bit controversial for us because there's no fixed concentration of A. In other words, if we are to look at times past the injection time, right? If we are to think about when we pulsed tracer into this reactor, we pulse it all in at T equals naught. Let's just call T equals naught the time when we pulse the tracer in. So after T equals naught, we are not pulsing any more tracer in. In other words, CA in equals 0 for T more than 0. So we can say CA in equals 0 for T more than 0. So this equation is simply minus CA over tau for T more than 0, right? And you might be saying, well, this is so unpleasant, more than 0 and all this, but you know, I can fix my time domain. I can say, yeah, T equals 0 is complicated. I'm pulsing tracer in, but so I want to simplify it and just consider times greater than 0. So if that's true, and we can see that's true from the mass balance, then we can integrate this equation. This is very easy to integrate. We can say this is simply a first order ODE, and this has the solution CA equals CA naught, whatever that is, times E to the, and this is going to be minus T over tau, right? So that's the solution. And of course, you know this because if you have any equation like this, if you have dx dt equals minus k x, then the solution to that solution is given by x equals x naught times e to the power minus kt. Right, so generally speaking, that's in fact, that's how we define E of the function E, right? It comes from trying to solve this equation. So if our equation is like this, then our constant here is 1 over tau. And so T times 1 over tau minus 1 over tau looks like this. So that is the equation we expect, right? So if we do a mass balance, that's our concentration of salt. And then as we said, E of theta is then what we get if we take the concentration of salt, so Ca of theta, and divide it by its own integral. So, and that's integrated over all possible values. So this is infinity. So this is Ca of theta in D. Keep forgetting to do it. Okay, so that was the expression we had before. So it looks like if we are going to progress this, right, for Ca of theta, that's easy. We can just stick this in and we use a theta. So the variable here is theta. Let's do it this way. So let's not disturb that equation. Let's just substitute this now. So this part, we are using t equals theta. Right, just because we are substituting, just because we are using theta here. So that is theta. And now we can see we need to do the same in the denominator. So we need to evaluate this integral. So let's do that. So we take this denominator and we say this equals, and first off, we can see that we can remove the Ca naught as a constant of that integration. So just extract that Ca naught here. And then the integral of the exponential of your function is equal to 1 over the constant. So it's going to be minus tau times e to the minus theta over tau. Right, and to just check this, differentiate it. When you differentiate it, you'll be multiplying minus 1 over tau by this. So you'll get a 1 here, and you'll get e to the minus theta over tau, which is the same as this thing, right? So you can confirm that's the integral. And we are integrating between the limits 0 and infinity. So let's do that. So at infinity now, right, when we stick in theta equals infinity, we are going to get e to the minus infinity over here. And what's e to the minus infinity? Right, that's 0. If you think of the exponential function, your exponential function, the pure exponential function looks like this. So at minus infinity, it's 0, okay? So at the upper limit, it's a 0 minus, and then the function at the lower limit. So at the lower limit, it's theta equals 0. So e to the 0 is 1. So all of this becomes a 1. So it's Ca naught times minus tau times 1. Right? So that's there. So that is nothing but Ca naught times tau. So that's what the denominator works out to be. So then we can say E of theta is simply this thing, right? The integral for the denominator we worked out here. So it's that. And then, of course, the Ca naughts can cancel. So the solution finally is 1 over tau. Let's just pull this off. 1 over tau times that. So that's for a CSTR. So E CSTR is 1 over tau e to the minus theta over tau. Okay. Any questions or comments on that? So it's an exponential decay function. and the decay rate, the decay constant is related to tau. So that's, we have proved then the exponential decay that we were looking for. Then that's of course half the story. We also want the I of theta. So let's see now. So far we've said I of theta is the same as E of theta. And in fact, we didn't take a minute to appreciate how crazy that was. I mean, if you look at this operation, you are integrating E and then 1 minus that and 1 over, it looks like there's no chance these two are ever going to be the same. And plus E looks like this complicated function here. So let's see what happens. So let's put this in as a new copy. Let's do this. So there's our E of theta function. Ugh. So let me just one of it. To the okay, so that's what we are trying to integrate, and this integral again, we want to integrate an exponential. We can just regard that as a constant. That's not a function in theta, so that can sit out there. And if we integrate this, again, it's going to be minus tau times all that. So this integral is simply minus tau times this. So all of this becomes minus tau times this, right? And we are going between limits. The limits were 0 to beta. It's 0 to beta, so from 0, and the upper limit was theta. Here it wasn't infinity. The upper limit was theta. So if we evaluate these limits, are there any simplifications? Well, first off, yeah, we can simplify things a little bit. So this minus 1 over tau and tau, this can become a 1 plus this. Okay, and so it's simply equal to that, right? So that's what we have here. So let's keep going. So now when we have theta, when we are at the upper limit, then this term is simply this one. By the way, that 1 minus, let me just check. Yeah, that. Why did I apply limits around this whole thing? Yeah, it's not right to put the limits here. Sorry about this. So the integral is only of this part. So I need to say here, this is theta. And so here, this part becomes, well, it's the same problem here. So we want to extract this. Okay, and then this part, yeah, this is the part where we applied limits, right? So you see, you have to be very careful. 0, 1. Okay, so that's right. And then, so this part, if theta equals theta, then obviously you get that part. Then when we apply the lower limit, then we have to say here minus. And then at 0, we've got e to the 0, which is a 1. So minus a 1 here, okay? And, oh yeah, this stupid thing. So yes, yeah, it's actually like that, right? So we've applied the upper limit where theta equals theta. So you've got the term surviving. And then the lower limit is a 0 where theta equals 0. So this is a 1. So the lower limit minus the lower limit, which is a 1 there. And then if you look at this, you've got 1 minus 1. So that, so those ones can cancel, leaving us with only the exponential part. And look at that. We now have the same function as before. So your e of theta is the same as your I of theta. So let's just copy this and write them next to each other. You might not be believing your eyes, right? So there's E CSTR and there's I CSTR, and they are identical. So even when we do this in a simulation way, we still find the feature of the CSTR. We've got the same on the inlet and at the exit, right? It's the same exponential function. You might be wondering, from such a weird operation to do on a function, how is it possible that we've got the same function? Well, it's because this specific function is an identity of this operation, right? So this is the only function which, when you apply this this whole operation to it, you'll get the same function. So this is an identity of this operation. That's a way to view that. So in maths, you are always looking for things like that. You are always looking for identities. So for example, if you look at vector matrix operations or vector matrix multiplication, the identity matrix is the identity of that vector matrix operation, right? So in this case, for this operation, this is the identity. So, but we didn't try and use that. All we started out with was saying, oh, it's a CSTR, and so that's the balance. And yeah, so the physics, it's not as if we used, it's not like I've done something underhanded here, right? I stuck purely to the physics of the problem, and we found the exponential functions we expected, and we found that they were the exact same function. Okay, any questions or comments on that? Okay, so now let's try and do the same thing for the PFR. And by the way, just a reminder, you might be wondering, what are we doing here? We started this whole section because we wanted to get away from the ideal cases, right? We wanted to deal with the imperfect mixed cases where it's not perfectly mixed, or it's not perfectly plug flow or perfect batch. Well, the reason we are still sticking to CSTR and all of that is because before we jump into the really imperfect mixing types, we want to check our theory in a way, right? We've derived certain expressions. We've derived some relationships between E and I and all of that. And we, as yet, don't have full confidence that this theory holds up. So we want to test it against the cases we do know. So we're just doing that right now, right? So that's why we are still doing this. Now, for the PFR, let's think about what we have here. So we are saying we are pulsing everything in here, and then at some time later after the pulse, so 0 is where the pulse was. So at some time later, everything comes out. And what is this time going to be? Would anyone like to guess a time for this? So think about it. Everything is coming out at that time. What time should that be? almost by elimination. There's only one thing, there's only one variable. Can you tell me what that one time should be?
Is it the space-time?
Thanks. Yes, that's what I'm looking for, right? That's the space-time. So remember, space-time, we said, is the average time that we spend in the reactor. So if everything is coming out at one time, then that must be the same as the average time, tau. So we are expecting our PFR, the exit RTD specifically, so E of theta. We are expecting a spike here, and that spike will occur at theta equals tau. Okay, so that's one bit. Then the other part is, how do we show the spike, right? How high is the spike? And here we run into a bit of a problem. It's a little bit confusing because this is not like a nice spike like this, you know, a spike that has a head here. It's a spike. It's a pure spike. Maybe I'm not saying very much like that, but maybe think about the fact that it's all happening in one instant, right? So when we pour our salt into the reactor, imagine that we did it with a flick of the wrist. So we really just dumped everything in one instant into that reactor. And we are really talking about it, you know. So let's say this, we dumped it into the PFR somehow. So at the inlet point, we instantly dumped everything in one shot. So it wasn't that we looked at the syringe, we pointed it there, and then we slowly pressed it down. So we didn't do this. We didn't slowly pulse it into the reactor, and then, right? We didn't do that. We dumped everything in one shot. So in one instant, everything is concentrated. And so if we do it that way, then that whole instantaneous shot will appear as an instantaneous spike out there. And a way to understand that is to say, well, if I took my time and I did it, if I injected slowly, then I would have some finite peak here. But then if I took someone who was much faster than me, or if I did it much faster, then that time would shrink and the peak would go much narrower, right? So then it would start to do that. So it's the same amount of salt. So the area under the curve has to be the same, but we are using a much smaller time to do it. So we are really concentrating everything into one instant. And so the smaller we make this injection time, the higher this peak is going to go. And in fact, if we are thinking of a theoretical spike, in a theoretical spike, we are allowed to say, we put everything in with a delta T of 0. So we instantaneously shoved everything into the reactor. So if that's the case, then this spike is a pure spike. It's going off to infinity. So that's off to infinity at a certain instant in time. So if that's the injection, then that's at time 0. And that also means at time tau, we are also expecting an infinite spike here. So we need a function to represent that, right? And it's a little bit inconvenient. We want an instantaneous spike. And Dirac has solved this problem. So in physics, this is a common problem where you want to talk about interfaces and you want to talk about everything concentrated into one instant. So Dirac has proposed this function, and it's named after him, the Dirac delta function. So we say delta equals, or delta tends to infinity. So Dirac delta in x, Dirac delta in x tends to 0 for x equals 0, and Dirac delta equals 0 for x how do we say not? No, that doesn't work. Oh, it worked. Okay, so for x not equal to 0, the Dirac delta function equals 0. So if we were to draw this plot, it would look like this. Okay, time to refresh here. So this is the Dirac delta function. So I'm choosing my 0 to be here. That's x. And everything is 0 up to 0. And everything is 0 after 0. But at 0, we have a discontinuity. And at that point, we jump discontinuously off to infinity. Right? It's a crazy function. But it has solved many, many problems in physics, to the extent that one of the physicists wrote a poem about this. He wrote a poem about how, I forget the thing, but he wrote a poem about how everything was so complicated, and then this Dirac delta function arrived and saved everyone. So that's what an impact this function has made, because now you can mathematically express the idea of instantaneously concentrating everything to one instant. You might also hear about the sea of Dirac, right? The sea, like the ocean. So the sea of Dirac, if you think about an interface on a surface, anyway, you can read about the sea of Dirac. So the Dirac delta function, though, it's like this. It's 0 everywhere except at 0, and at 0, it's going off to infinity. So it's really a broken line. So we should show broken line. Okay, and it has yeah. So that's what I mean by a broken line here. And there's a special property of this function, in addition to the, right, this is special enough, but there's another property of this which makes it suitable for us for modeling RTD. It has this crazy property, which is if you integrate it, you integrate it over minus infinity and plus infinity, then it integrates, crazily enough, it integrates to a 1. So the area under this curve, if you can call it a curve, is a 1. Now, clearly, you are not getting any contribution to the integral from here or here, right? These are pure zeros. There's no area from this part. So that area of 1 is the area sitting under this point, under the single point, this unimaginably small space, right? It's not like I'm saying this is 0 and oh, there's 1 here and minus 1 here. No, this is what do we say? This is, like we talk about an instant in time. This is a point in space, an actual point, not a differential amount or anything. This is a point in space. So sitting under, so this point is going off to infinity in such a way that the area under this point is a 1. So the Dirac delta function, it's not just this. This is, in a sense, easy enough to do. But then to say, well, it goes to infinity in a special way such that the area under that point is a 1, then that fully specifies what we are looking for. Then we can say E of theta is nothing but the Dirac delta function. So the Dirac delta function of theta. But of course, if we say theta like that, then we are going to get a spike at theta equals 0, which is not what we want. So we shift this by tau. So we say E of theta equals Dirac delta of theta minus tau. And that gives us then our pure E of theta. And I'm going to cheat a bit and use this figure. So E of theta. So this is no longer the pure Dirac function, because now I'm going to shift it. My E has shifted me to tau. Right, so at tau, everything exits in one instant. And so that is a suitable definition for what we talked about earlier. Okay, any questions or comments on that? So that is the exit RTD for a PFR. Now let's look at calculating the internal RTD. So again, we have this nice relationship, okay? So that relationship applies always. We said there were no assumptions there. So, and we should just point out this is for the PFR. And so I for the PFR. We get by substituting for EPFR here. Okay, and so let's think about if we are integrating different values of theta here. So first off, well, let's do it with a sketch here. Maybe a good way to do this is like this. So we want I of theta. So let's think about what happens as we integrate in this way. So let's think about points all along here to begin with. So just before tau. So, well, let's just make one tau here. And so if that's where tau is, then if we pick any theta value to the left here, so let's say we pick a theta value here, the integral of E of theta, we can see up to this point is 0. The function E is 0 up to any point before tau. So if you look at this formula, when we are integrating for any theta value less than tau, this is going to be a 0, right? And so we are left here with 1 minus 0. So this is just 1 over tau. So we can say here, this equals 1 over tau. 1 over tau for, sorry, I'm getting, hope Word doesn't crash on me. Okay, so this is 1 over tau for theta being less than tau. And then let's see what happens when you get to tau. Then instantaneously you have that whole area of 1, right? So as you integrate across this, you suddenly pick up an extra area of a 1, right? So if you look at our formula, when theta goes past tau, then this whole thing becomes a 1. So then it's 1 minus 1, and that's 0. So we can say here for for theta more than or equal to tau is equal to 0. Okay, so that's the function. It's saying it's constant up to tau, and then after tau, it's 0. So if we draw that, it's constant at 1 over tau up to tau, and then after tau, it's 0. And let's just put this in also. Of course, there aren't any points on this. This is just to show it is continuous, but not differentiable. Right, so that's what we get for I of theta. And if you think about what we did intuitively earlier, right, when we were imagining the possible solution, this is all exactly what we said. I've lost that thing. Let's see, where is that? Is that here? No. Geez, where are all the drawings for this? Where have I been saving? Place. So when we drew these curves earlier, right, we were trying to anticipate what we would get. We did predict the spike, and we did predict it would be constant and go down to 0. And that is what we have now, right? We've got a pure spike here, and we've got constant and then drop down to 0. Okay. Any questions or comments on that? And then, in a way, for the sake of completeness, what about our remaining friend, the batch reactor? Right, and this is a bit of a weird one now. So the batch reactor, of course, we charge everything into that reactor initially, and then we just let it keep reacting. So there's no exit that we can talk about realistically. We can't really define, there's no exit stream to measure an exit distribution from, but we can talk about an internal age distribution. Now, of course, everything is all together sitting in this batch reactor. So everything has the same age in the batch reactor. So we anticipate we do get a spike in the batch reactor case, not a finite spike, a pure delta Dirac type spike, but you'll often see me breaking this beautiful picture and drawing ugly spikes here. But it's a Dirac spike, right, in the batch reactor. But it's also a moving spike because things are getting older as time is passing in this batch reactor. In the PFR case, of course, things are also getting older there, but they are passing out of the reactor. So they leave, and then so everything, remember, the tracer only represents one element of fluid. So constantly, as the water is passing through, every element of water that enters will leave at the same time tau. So by the end of the day, all these curves E and I are of the water. We use the salt as a way to estimate what's happening in the water. So by the end of the day, it is about the water or the fluid in the reactor. So this fluid in the reactor is constantly replenishing itself. So it's constantly exiting with that one age. Whereas in the batch reactor, there's no replenishment. Everything is sitting there all the time. And so as time goes on, this whole collection of molecules is just getting older. And so the same spike just marches its way along like that. So the batch reactor doesn't have a steady internal RTD. There's a moving spike. So the spike moves along in this direction at the rate of 1 second per second. Any questions or comments on that? Okay. So that's those are the ideal types. And then we can start thinking about more interesting cases. One other thing we can do is calculate the mean residence time. We've already said the area under this is a 1. So we can say the average age, so beta bar, the average age is equal to, and we'll use statistical averaging methods here. Should have done it like this. So if you do statistical averaging, so if you take any probability function, if you want to know the mean value of any property of the function, you just multiply the property by the probability function, because remember, this is the fraction. Remember, E of theta delta theta is the fraction of fluid elements of H theta. So if you multiply the fraction by the value itself and then add them all up, this is like the weighted sum of theta. So you get the average theta value by doing this operation. And so if you look at for the CSTR, what we have, that's equal to 1 over tau e to the minus theta over tau. And if you do integration by parts, you can show that this equals tau. Yeah, I'm just a bit worried about time here, but it's a fun little integration to do. It works out quite easily. So see if you can prove theta over bar equals tau. So you can prove theta over bar equals tau. And then if you do the same for the PFR, you will also get theta over bar equals tau. So you can prove that the average age is the same as the space-time. I think I'll just put out some notes about that. Okay, we'll come back to this CSTR PFR in series. For the laminar flow reactor, this is another one that you can just read about. So let's talk about the physics of the problem instead. So let's just cut this out. So if you think about this laminar flow, you have finite velocity everywhere in this pipeline. Right, so in this pipeline, we have a certain maximum velocity. So if it's laminar flow, your center of velocity is of course going to be the maximum, because that's the furthest away from the wall, right? At the wall, you have zero velocity, right? It's a no slip condition at the wall. So V equals 0 at the wall, and then V is some number in the center. So it's some maximum in the center. So let's think about when we would first start seeing anything appearing at the exit. So you pulse your tracer in here, and then you wait at the exit to start seeing tracer. So when is the earliest you'll start seeing any tracer from this, this laminar flow? Any takers? How long, what's the fastest you will exit from this reactor? Right, so we've got theta here, there's E. So maybe to ask it as, can we expect anything to appear immediately at the exit at age 0? So having spent no time in the reactor. So if we look at this, nothing is spending no time in the reactor, right? The center line, it is the fastest, but it's not infinitely fast. So even the center position takes some finite period of time to reach the exit. And then at the wall, you have zero velocity. So everything that gets stuck on this wall never ever exits. So you can wait till infinity and you won't see the wall stuff. And then everything else is in between those two extrema, right? So you've got some maximum velocity, but finite, and you've got some zero velocity. So you will have the earliest contribution from here. So you'll start seeing something here, right? So this point is where you are getting some material from the center position. So everything was zero up to this point, and then you will start getting a contribution from the center line. And then all these other radial positions have lower velocities, so they will come out later on. So we expect that kind of profile. And so it almost looks like a PFR in series with a CSTR. That's not what it is. This is not an exponential decay. This is actually a cubic decay. And if you follow the derivation here, it's because we have this this parabolic velocity profile. So we know in laminar flow we have a parabolic velocity profile. And if you apply that, so you basically calculate the time taken, the residence time taken at each radial position. So we do know the velocity at each radial position. So you can translate that into an age for a radial position. And then you can work out d theta dr, and you can use that to estimate the fractional contribution at the exit. And so you can interpret that then as an RTD. So that's what you get for E of theta for laminar flow. And then if you think about I of theta, so for I of theta, remember 1 minus, so everything will be held up until a certain point, and then you will start to lose material to the exit. So I of theta looks like that. So that's a laminar flow reactor. Then let's think about a PFR in series with CSTR. So we are feeding here and they are in series like that. So again, the way to figure out what the result of that is going to be will be by imagining if we pulse some tracer in here, and then we imagine what will happen at each stage. So if we pulse tracer in, and this is obviously, we define that pulse time to be at t equals 0. If we pulse tracer in, then that whole trace will be delayed by a PFR. So our PFR will shift it down to tau. And so we did say that before, but now let's define that tau. So this tau, we'll call it a tau p, right? Because now we have two reactors here. So they will have different residence times. V over Q is different in each case. It's the same Q, but maybe it's a different V. We don't know. So the same Q, but this one is a V PFR, and this one is a V CSTR, right? Stirred tank reactor. So we can define a tau P and a tau S. So we pulse in at time 0, and we'll start to see a pulse coming out at time tau P. And then if we think about this pulse entering the CSTR's influence is to exponentially decay this, right? It will do its serial dilution. And so we will end up with an exponential decay from the CSTR. And so we will have here a tau P. Everything is delayed until tau P. and then it shoots up to some value, and then we see an exponential decay after that. So that's what we expect from the from PFR in series with CSTR. So here's E, here's theta, here's tau P, and the curve we expect is it's 0 up to tau P, and then suddenly it appears, everything appears here, and so everything now enters the CSTR, and then we instantaneously mix and start seeing contributions at the exits of the CSTR. It gives us material immediately, and then it decays out. Right, so that's what we expect, PFR and CSTR. What if we reverse that? So let's say we put the CSTR first, and then we do the PFR. So we know we're going to draw something there. So there's the PFR. So again, we are going to pulse in here at t equals 0. We will pulse in at 0. And now we are exiting the CSTR. So from 0, we will get an exponential decay. And now we are feeding an exponential decay into a PFR. And what this PFR will do is delay every single part of this curve. So this whole curve is going to be delayed by a set amount of time. And that set amount of time is tau P. So in the case of CSTR first, you get the same curve as over here. So you get the same E of theta function. So it doesn't matter what order you put these in, you will get the same RTD. So the RTD is actually the same no matter which way around you do it. That's not the same as before when we were looking at conversion, right? Remember when you put I think it was the PFR first, then you had a better overall conversion. In the case of age, it doesn't matter which way around you do it. Okay, so that's one. Just save that. Now let's think about another case. And maybe we want to take a break here, but let's think about a case like this. Let's say we have a CSTR. Okay, let's do it like this. Let's say we have a PFR here. And then we have another PFR. And maybe this one is a bit smaller. And now they are in parallel. Let's do that. So what's the RTD going to look like in this case? Well, let's define first our tau P1 and tau P2. So one of the things we can say first is, or one of the things we can think about is, which one is bigger? Is tau P1 bigger than tau P2? So that's the average time that you spend in the reactor. Let's assume also that the flow rates are the same. So our total flow in is 2Q. So the tau is V over Q. So if this is a bigger volume, then it is a bigger space-time. Or more physically, if we have the same flow rate crossing a bigger space, it's going to spend more time there. So there's more time spent here. So tau P1 is here. And tau P2 is somewhere here. And then we can imagine, always we use the thought experiment. We pulse some tracer in, what happens? So the pulse goes in here, it's on 0, but then it gets delayed here by tau P1, and it gets delayed here by tau P2, which is less. And then if you add these two together, you are going to get simply 2 spikes like this. 2 spikes. So that is what CSTRs in parallel look like. Okay, if you were to plot the I of theta as well, I remember the integral. So when you integrate over here, you'll get nothing. So everything is retained. In other words, whatever was in the reactor here was retained by both until you reach tau P2. So at tau P2, you suddenly lose everything from that first reactor, from that second reactor. So you lose everything from that reactor, but there was still some held up in the first reactor. So this doesn't go all the way down to 0. And now when you reach tau P2, then it does go down to 0. Now you really have lost everything. So that's tau P2. So that's I that we expect for PFRs in parallel. Then let's think about CSTRs in parallel. So if we have CSTR here and CSTR here, let's draw it smaller. Then the same applies. Tau S2 is less than tau S1. And what we have now, again, the thought experiment, spike coming in centered on 0. And what will come out here is an exponential decay from 0. We'll also get an exponential decay here, but they will decay at different rates. So let's draw this more carefully. Let's put down some axes. And if we have a lower tau value here, then from, should have been using, so this is 2, okay? So from reactor 2, we will have an exponential decay with a smaller space-time. So we are going to get something like this. It's going to decay pretty quickly like that. And then from the other one, we are going to get a much different decay. So we'll still have an exponential decay. So that's reactor 1. So we'll still have an exponential decay here, but it's more like that. So this will be a shallower decay. Because if you look at the equation, it's 1 over tau e to the minus theta over tau. So if your tau value is large, then 1 over tau is small. So it will decay more slowly. So you can see a slower decay here. And your 1 over tau will also be smaller. So it's a lower value. So that's like tau p1, right? Tau is larger. Tau p1 is larger. So 1 over tau p is smaller. So it starts slower, but it decays more slowly as well. So the superposition of these two then is what you will be observing here. So your final curve is the sum of two exponentials, which is something like this. So the sum of two exponentials is not exponential, right? Unless they are equal, then the sum of two exponentials is twice an exponential. But otherwise, the sum of two exponentials, you'll get a curve that's dominated by the fast one down here, and then a curve that's dominated by the slow one there. So yeah, it's like a two-curve supposition, two-curve superposition. Okay, so that's CSTRs in parallel. Then try and imagine this case now. Imagine that you have a CSTR and let's imagine that we have a flow going through here and some of that exits, but some goes around like this. So it circulates back this way. It enters a PFR here. And then it does that again. Okay, that's one exercise. Let's think about, okay, let's do it with two PFRs instead. I would like you to try this out. So maybe let's take 2 minutes. So take about 2 minutes and try and sketch out what you think this RTD is going to look like, right? I'm talking about this one down here. So sketch out what you think this RTD is going to look like. So let's just take a minute for that. Okay, so did anyone come up with anything interesting you want to share there? So of course, the way I'm going to figure this out is start with a spike at 0 and imagine what happens to that spike. So that spike is going to flow up this direction. It's going to be delayed here by tau p1. So let's label them tau p1 and tau p2. And so it's delayed by tau p1. And then part goes off over here. So part of that trace will exit at tau p1. So you get a spike here, right? And I'm just going to call that 1. But part is going to keep going down here. And that will get delayed by tau p2. And then that will make it up here again. Now we are not receiving any more salt. By the time the recycle gets here, we are past the time when we were contributing salt. So now it's just the recycle. So we've got a recycle now coming through that has been delayed by tau P1 plus tau P2. Then it gets delayed by another tau P1 and then some exits here. So we get another contribution here. And then again, we get part of that recycled again. So a second pass recycle. And then we will get some going out here and some passing through here. So we get a third spike here. And each time these are being delayed by a period of tau P1 plus tau P2. I'm just writing it as 1 plus 2. So we get a kind of sawtooth, well, not sawtooth, we get a kind of tooth here of a series of teeth. And if you look at the maximum, it's like an exponential decay, but it's an interrupted exponential decay. And one of the explanations I have for that is if you take this thing as a whole, right, this as one reactor, then this part here with the recycle, that's like the CSTR, but it's a CSTR that's interrupted by PFRs in the middle there. So that's one of the interesting RTDs that you get. Okay, so that's on the. So that's what we can do for combining reactors together to get the real world cases. So that's why we are doing this, because in the real world, what we could do is say a real world reactor is actually a combination of different ideal reactors. And that was one of the comments we made, when was it, yesterday? We said that if we look at a real reactor, we would see regions where there was a high circulation zone. We would see regions where there was a straight through pass, as if it's a plug flow reactor. We would see regions where there was good mixing and good flow, like a CSTR. So we are saying now that we could take a real reactor and create some combination of the ideal reactor types. So this is one strategy that we could adopt. We could decompose our real reactors into a combination or a network of the ideal reactor types. And the advantage of doing this is we can then add up the contributions from each of these reactors, and from that calculate the overall conversion. So the difficulty with working with a case like this is that we don't have a clear model to work with, right? In this case, we don't know what to do at all. We don't know how to write the balance in this case. But in this case, we know how to write a balance on a CSTR or on a PFR. So the only thing that is unknown here are these volumes. So, so we need to know this volume, VS1, and this is a different volume, VP1, and this is a different volume, VP2. And these are virtual volumes, right? These volumes are, if you think about the real case, these are just imaginary volumes in some real reactor. But still, imaginary as they are, we can imagine a kind of line here, a surface that separates these two zones. So we can think about different zones in the real reactor. And the reason that we are doing this is if we can measure the RTD, and we know we can always measure the RTD, all we need to do is pulse a little bit of tracer in here, and then we measure out here some series of curves, and then we know something about the features. We know if we see a spike here, then that is the spike of perhaps one of the PFRs. Or if we see an exponential decay, then we know that's the exponential decay from a CSTR. So we can always go ahead and measure an RTD, and then we can use the features on that RTD graph to estimate the volumes and the flow rates through this network. And we did in the very second week, right? Very first week or very second week, we talked about solving the conversion in a network of reactors like this. So that's the point of RTD. We can take a real situation, which might be quite complicated, and we can propose a network of reactors that looks approximately similar to that. So we produce a network of the ideal reactor types, and then we can figure out the relative amounts in each of these reactor types by measuring and interpreting an RTD. So we'll be looking at that in the tutorial on Friday. Okay. So that's about as far as I think we should go today. And then, of course, you've been patiently waiting to find out about the test. And the reason I didn't send out that email or well, let's just, I guess this is not part of the general. So let's